Sodium batteries are catching up, a breakthrough for cheaper, cleaner energy storage. A new metastable sodium compound with record ionic conductivity brings low-cost, sustainable, solid-state sodium batteries closer to reality, challenging lithium's dominance. Solid-state batteries promise safer, more powerful energy storage by replacing flammable liquid electrolytes with solids. Today, most rely on lithium, which is expensive, scarce, and environmentally damaging to mine. Sodium, by contrast, is abundant and cheaper, but sodium-based solid-state batteries have long struggled to match lithium's performance at normal or low temperatures. If you like my content and want to listen more interesting science stories like this, then subscribe my channel and don't forget to like and share this video with your friends and colleagues. A new study led by Shirley Meng at the University of Chicago's Pritzker School of Molecular Engineering, published in Joule, takes a major step forward. The team developed a sodium hydridoborate-based solid electrolyte with a previously unreported metastable crystal structure. This material exhibits ionic conductivity over an order of magnitude higher than past sodium electrolytes and 3 to 4 orders of magnitude higher than its precursor. It performs reliably from room temperature down to below freezing, setting a new benchmark for sodium solid electrolytes. It's not about sodium versus lithium. We need both, said Meng. This work moves us closer to a future where the same gigafactory can produce both chemistries side by side, stabilizing a new structure with established techniques. The breakthrough centers on stabilizing a metastable phase of sodium hydridoborate using a straightforward heating and quenching process. Heating until crystallization begins, then rapidly cooling to lock in the high conductivity structure. Metastable phases are common in materials science but had not been applied to sodium solid electrolytes before. Because the method is already used in industry, it lowers barriers to scaling up. Established techniques make industry adoption easier, explained first author Sam O of A***. New processes often face resistance. Here the path is clearer. Thick cathodes for higher energy density. The researchers paired this metastable electrolyte with an O3-type cathode coated with a chloride-based solid electrolyte. This allowed the use of thick, high areal loading cathodes, reducing inactive material and boosting energy density. The thicker the cathode, the higher the energy density, O noted. Previous sodium batteries relied on thin cathodes to offset poor ion transport, but this new design overcomes that limitation. Why this matters. The discovery addresses 3 key challenges. 1. Performance. Exceptional ionic conductivity enables stable operation across practical temperature ranges. 2. Cost and sustainability. Sodium is plentiful, lowering both costs and environmental impact. 3. Scalability. The synthesis relies on proven industrial techniques, facilitating rapid adoption. Together, these advances make sodium-based solid-state batteries a realistic complement to lithium systems. They could power electric vehicles, grid-scale storage, and electronics more affordably and sustainably. It's still a long journey, said O, but this research opens the door for sodium to stand alongside lithium in the battery landscape. Outlook: complementary chemistries for the future. As demand for batteries surges, no single chemistry will meet all needs. Sodium offers particular advantages for large-scale, cost-sensitive applications. By stabilizing a high-performance sodium electrolyte through a practical method, this work provides both a scientific breakthrough and a clear path toward industrial implementation. It exemplifies how fundamental materials research can unlock sustainable next-generation energy technologies, paving the way for cleaner, cheaper batteries that work alongside lithium, not against it.